let's start.
Yeah, so the QR code is correct now. Sorry for that. So let's begin. So hi everyone, I'm Joel. I've been with Nubank for 4 years now, and I just moved to the Datomic team about 8 months ago. I work with Filipe. I work with our guy Jared here, who handles support every once in a while, and I am, so fun facts about me, I'm married to another Nubanker who's also here, and before Datomic, I helped do a lot of stuff at Nubank. I still do a lot of stuff, like country registration table, for example. We have 2 dog kids, Princesa and Urso, and I recently started riding and jumping horses. I'm not jumping yet, though we're working on that.
I'm Filipe. I'm married too. I have 2 kids, a boy and a girl. And the picture shows me playing guitar with my band, heavy metal, I like it. And this picture is a little old. I came from long hair to any hair. So, and I work in the Tom team. Before I joined the Tom team, I was working in Nubank building distributed systems for Pix, that's a payment method, Brazil ledgers payment method that you can transfer money between Brazilian accounts. And anyways, I think let's start the talk today.
Yeah.
And we'll talk about Operating Datomic at scale with some tuning techniques and also some features that help you to troubleshooting performance.
Yeah, and before I start, we will have some QR codes around the presentation so that you can refer to documentation, things like that. I also want to say that this is our first time doing a presentation. We really happy to be at Conj, so thank you everyone for the opportunity here. So what scale are we talking about? So as you might have seen from Bruno's presentation, it's a huge scale. We have thousands of databases. We just surpassed 80 million customers this week. And we have some databases reaching 100 billion datoms.
Yes, and we need to scale fast. Nubank has just 10 years, and we have more than 8 million of customers.
Yeah, and sometimes we just need to launch a new country. We get a banking approval, banking license approval, and we just have to do it. So we'll talk about 2 features of Datomic. That's query stats and IO stats, and how we use that at Nubank, because of course, as we work with thousands, tens of thousands of transactions per minute, every millisecond counts. So we have to be really mindful of that. We also are in a huge drive to reduce costs with AWS. And we did that with some trick about tuning. And we also tried out a little bit ZGC to improve the transactor throughput.
So the presentation will be divided into 2 parts. First one, using query stats, IO stats. The second part will be fine-tuning using ZGC and also tuning memory index to reduce cost. So
the first problem I want to talk about is a problem that query stats helps you to solve, and that's ordering of clauses. So you should always put more selective query clauses first, and basically we'll try to illustrate that to you and how important that is. So we're basically removing all those red dots, which is like unnecessary memory consumption and computation, and we're doing that with the help with query stats.
This is the way you can enable query stats. You can follow the version, and also the QR code points to the documentation of query stats. If you want to see more about that, you just need to use query stats true in your d-query API, passing it inside the query map.
Yeah. So just a little disclaimer.
It adds overhead, so you need to be careful when you're using it in production.
Yeah, this is a tool mainly for development, like optimizing your queries, not to like keep it enabled and see how your queries are doing every time. And we'll also look at the map, so you'll see that it doesn't make a lot of sense as well.
Yeah, in Nubank we make a trick to do that. It's showing the diagram for you of your architecture.
It looks like our legal team got a hold of this.
Oh man.
Yeah, we cannot share it.
Sorry.
But basically what we can say is that we take advantage of Datomic's peer architecture, and we just have an endpoint that simulates a production peer, and we can run any query on that without affecting production, without putting anything on the hot path, right?
Yes, just because they don't have a peer architecture, so you can have a peer totally independent of the production flow.
So let's continue. We got a fairly big map, and that's why I'm saying like it doesn't make a lot of sense to use it in production every time. So what I wanted to highlight on this slide is the schedule part, which is just a list of your query clauses. And that's basically our ordered list, how Datomic interprets it, and how it's going to process your query. Don't worry about that ground thing there. It's just an internal representation of it binding your variable, your argument that you provided to the query to an actual variable, Datomic variable. So the query here that we used, it's John Lennon releases. So you can see that he has 21 releases in our database. This is the music frames database that we use a lot for benchmarking and stuff. And it gets the 21, and then it starts to bind the release name to the album name variable that's going to be returned. And a good part of that work is dropped because we are only interested in releases before 1970, and that's our green stuff here. So what we did is, like, if we inverted the clauses here to put year before, and just because we know the year of every release, so there's no reason why not to filter and not do a lot of work.
Yeah, the interesting part that is the arrows. You can see that we just inverted the clause orders, and all the unnecessary job was proved. So we don't need to get a lot of data before to have exactly the restrict clause that we are querying about.
Yeah, and it might not look like much in this query specifically, but when you're talking about, like, we have a huge database with 80 million customers. How do we not do 80 million times the same work if we only care about customers under 30 years old or something like that? But then the problem that you might ask is, okay, but if I'm not supposed to use it in production, the map is big, it doesn't have any numbers in it, like any timings in it. How do I find out which query I want to optimize? And that brings us to IO stats.
Yeah, you can use IO stats combined with query stats, because with IO stats you can make clear what is the transaction or query that's problematic, and then you use query stats to look at the query and then understand how it's being interpreted by Datomic to do the necessary adjustment. Yeah,
and basically at Nubank we use Splunk to query it, and then we got, okay, let me look at this service, which queries take longer, which queries are maybe putting us at risk at crossing SLA or something like that, and then we put query stats on that and look at it. We also can look at transactions and the caching setup, which we'll explain a little bit now.
Yeah. You can enable IO stats by using the IO context providing in the -d/transact API or in the d/query.
Yeah, and you can also look at the documentation. There's lots of other APIs that support it. So.
Yes, exactly. There are other, you can see the data documentation. Yeah. And also, you can enable both if you want in the d/query IO stats and query stats.
And you can also enable it in nested transactions. So if you have a transaction that does database functions, you can enable IO stats in the database function in a query and look at the map combined with everything. So again, what we get is a big map. And yeah, there's a lot of numbers here, and we'll walk through a little bit. So one of the numbers that we want to highlight here is API mass and MSAC. API mass is basically the transactor doing the actual work for that transaction. So as some of you know, Datomic is serial, so it puts transactions on a queue, and at the time that it enters the queue, it starts counting the MSAC. At the time that it processes and does database functions and stores it in Dynamo, Cassandra, whatever, it's then API mass. And API mass also considers the reads, so if Datomic has to deduplicate stuff or do uniqueness checks, that's also in API mass.
Yes, important to say that about that picture is that the MSAC doesn't include the time of network between peer and transactor. So if you want to measure that time, you need to measure by the peer.
Yeah, yeah, so add a time function or something like that. Another thing that we found at Nubank is that we were transacting like 2, 3, 4 datums, and we were looking at 400 segments. So what is a segment? A segment is just an index segment, which holds like 1,000 and some datums. So why are we doing that? Because we found that some systems were submitting a whole entity. So like, let's say I have a customer entity where I have like the home address, the income, and things like that. And I want to change the income. And we were submitting the whole customer. So Datomic had to look at all that attributes and then say, well, okay, I only changed 2 datums. And that's work. That's work that is affecting the other transactions, that is making the whole system slower. And we also have been using IOStats to look at our caching setup. We also have our documentation about caching there. So basically, Datomic allows you to plug in a number of different caching layers. Some of them are optional, like memcached and volcache. But some of them are built to Datomic, like object cache. And of course, you want to always query the one that is closer to you. In that case, object cache or volcache. You should never go to, you shouldn't really aim to go to your durable storage much, because that's the one that is farther away. That's usually the slowest.
Yeah, the way you can see the interpret the return of the IOStats is that it try first to look up at the cache that's in memory and in the heap, and then if it didn't find the data, they go to the next cache layer. As you see the picture, the number represents how many segments was requested and how much segments was retrieved.
Yeah, and so the reads will always show that Datomic asked Ocache for 434. Ocache replied and said, well, memcache, I don't have 9, so ask further away. Memcache said, I don't have 8 of them, so go ask DDB. And that's what we represented in the image.
Well, I hope it is fine.
Yeah.
Now, because we will start to talk about some tuning.
Yeah.
Because the word is not make about features only.
Yeah, and some people don't care about features. They just want to see it work. So the first thing that we did, we had some problems with spending a lot of money on Dynamo, or spending a lot of money on AWS. And what we found is that the indexing job, which is what Datomic does periodically to create the durable indexes. So Datomic has 4 indexes, and the datums are usually stored in the transaction log. And then there's the indexing job, which basically creates the new indexes. What we found is that at some point in the number of datums, no spoilers. At some point in the number of datums, the indexing job cost starts being driven by the number of, by the size of the database and not the amount of novelty that you have. So not with like the actual things that need to be indexed, but basically just restructuring the index trees to fit the new data. How much is that? About 1 billion datums, what we found. Could be less, depending on how much data you have, how big your datums are. But that's what we found there. So you might ask, okay, so if I'm delaying the indexing job, is new data slow to query if I don't have indexes? No, and that's because I lied in the previous picture. You have another layer that is built in, and that's memory index. Memory index stores the actual datums that were recently transacted. So that's the first thing that it will ask. Say, well, is this recently transacted? Can I get it from memory? This is still technically a lie. We still have the entity cache and some other stuff, but let's keep it simple.
Yeah, basically, we have 2 knobs that we can move. That as the indexing job is start when the memory index reach the threshold defined. So we can increase the threshold, move the threshold, and index max. The threshold is the point to start the indexing job, and the memory index max is the point where the transactors start to apply back pressure if it's because it's overloaded.
Yeah, so what we did initially, and that you might find still in the documentation, is we recommend the threshold to be much lower than the max because that's safety. If you reach the max, the Datomic will just say, well, I'll not take any transactions, I'll just complete my indexing job, and you stop. But what we found is we could make the indexing job very quick with parallelism, with all the new stuff, like Dynamo is really fast if you are just throwing data at it. So we just moved the index threshold a little bit higher. And what we found is it was linear to the amount of indexing jobs that we were performing. So we had systems that were just indexing back to back, like completing an indexing, starting another one, completing, starting. And we moved from 20, 30 indexing jobs a day to 4. And what that did is this with our cost.
There's no number here, but I'm sure that the CTO know how much we saved.
Yeah, CTO, the finance department, they'll know. They will know. Yeah. So basically, this is storage bytes. That's just from Splunk. It roughly translates to write capacity units or any kind of write unit that you might have on your underlying storage. Of course, there's like batching going on. There is roundup and things like that. But that's basically what we translated. And if we do the math, it's around that. So what is that graph showing? That's 50% savings in writes to storage, and we're still ACID. Like we're not violating any ACID properties here. We still have the transaction log that is always being written. We still have all the security, everything. It's just the indexing jobs that we're messing with. But of course, as all things in life, it's not free. Memory is not free. Memory usage increases everywhere because, as you may remember from that earlier picture, memory index is replicated across all the peers. So if you have 10 peers, those 10 peers will have more memory usage. And the peers will take longer to connect because every time a new peer starts up, connects to the transactor, connects to the database, the transactor tells it, well, I haven't done an indexing job in an hour, so you have an hour of data to catch up. It's not that big of a deal. What we found is it was pretty much linear, but depending on your usage pattern, you could time it, like let's start more peers after an indexing job or something like that. And you can work around this. And memory, at least in our case, was much cheaper than writes to Dynamo. So for us, it was a pretty good savings number.
Yeah.
But it's not about quick tricks only. We did have some dark magic.
Yes. We also do some black magic.
Yeah.
This the Datomic log GC represents, it's a log enabled by default that you can see all the information about a GC performed by JVM. It's enabled by default, and you can see the properties that represents some phase of JVM, the event, and the duration. Yep.
And so I know we have the GC log for the JVM, which is much more complete. But for our purpose here, this served as well. This is the most important part. So GC cause will tell you what phase of execution your algorithm is doing. And then you can refer to the Oracle, open the JDK documentation and say, oh, this is a stop the world. This is a concurrent cycle. This stops only one thread, things like that. And of course, the duration, because you want to see how much you're doing GC for.
Yeah, with the two information, we can combine it. We can understand what phases was stop the word pause and how long it takes.
Yeah.
And then we search it and generate a graph that shows that we are spending a lot of time in stop the word pause in our transactors.
Yeah, and as you may remember, transactors are serial. So if you are spending time on GC, that's time that you are not doing transactions. So what we found is 114 hours spent in GC pauses per day. And that's because days at Nubank have 400 hours. No, I'm just kidding. That's a sum. But we did a trick to exaggerate that and represent this a little bit
using IOStats.
Using IOStats. And that's basically 184 million transactions that we could be doing, and we are not. Of course, this is exaggerated, but.
Well, technically, we rely on large heaps because we want everything to be close to the memory as possible. So when you have a large heaps, the size, the pause time increase as how much object you have. So it increases linearly. So we use an approach to resolve this problem.
Yeah, so basically what people usually see is I have a lot of pauses. I will increase my heap. I will put more CPU. But it's not just that. Like we also need to look at the algorithm. And before you throw rocks at us, because I know GC algorithms are pretty heated, with the ZGC. And so we were using G1 GC. That's usually, I think that's by default in every transactor. The punchline is that it guarantees low latency GC, so it tries to keep pauses under a millisecond. And it also does a lot of parallel work, so you have a lot of cycles that happen parallel, and then you don't get your computation much affected. Of course, you are affected because it's resources.
Yeah, and it has increased the throughput of the transactions in average at 33%. Yeah. And also, we noticed that it also decreased, in fact, the latency time of the transaction because we've got faster transactions.
And again, you might see, okay, so indexing job sucks because, like, look at this thing. But this is like millisecond, and as I said, like we have systems with like 10,000 transactions per minute. Like a microsecond could sometimes make a difference, especially on Black Friday. So it gives us faster transactions overall.
But it's not free.
Again, as all things. It does a lot of work in parallel, so you might need to increase your CPUs. You might need a little bit more memory because basically what ZGC does, it allows you to write a little bit closer to the sun. So it allows you to grow your memory usage a little bit higher. And because it knows like I can do like parallelism, I can pause under a millisecond and I can clean up a lot of things, so you can just use it. But I think that's pretty much, but you know what's free? Datomic.
Yeah.
Datomic is now free.
This is free now, man.
Yeah, so just to wrap up, like you remember from the early morning? And again, you might imagine Rich here right now saying, what's the problem? So when you are doing especially tuning, be problem-oriented. Like don't just, let me just switch this GC algorithm on this service that processes like 10 million transactions a day and see what happens. No, like be problem-oriented. Like look at, okay, we have a problem. We are too close to an SLA. We are at risk. And when you want to try it out, like spin up a test system. Datomic is free again, so you can spin up as many test systems as you like.
And we also are here to help the Datomic team, if you pay for support, of course.
Yeah. I'm just kidding.
But we have a great community in Clojure and Slack. A lot of people collaborate together there, and we are ever around too.
Yeah, Filipe is there every time. I try to be there sometimes as well.
George is there a lot too.
George is there as well, so you might have seen some announcements from us there. By the way, half of the Datomic developer success team is Brazilian now, so we are distributed just like Datomic. And a word from our sponsor, Nubank. So if you want to learn more, we would love to reach out. We are doing a lot of sharing of our internal processes, our tips and tricks Some of you saw Bruno's presentation about our engineering principles. And we are also sponsoring Clojure, of course, so we really care about the open source community. Greg, you might know him as Eric. He's talking about Clojure LSP tomorrow, which is another project that he takes care of while working at Nubank. So big thanks, everyone. I hope you enjoyed this day of Conj. I hope you enjoyed game night for you that are staying, and you enjoy tomorrow as well.
Yeah, and here, have some contact information. If you got interested, please reach out.
Yep.
Thank you.
Thank you.